Hi guys, this is Mrs. Foy, and this is a lecture about the history of the atomic theory and how the atomic theory has changed over time as we have learned more about the scientific evidence about what an atom is made of and what an atom looks like. So I'm going to tell you that exciting story today, and hopefully you are taking notes on your note sheet that was provided for you in Google Classroom as an assignment. So why do we use models anyway? What's so important about a model? Well, models help us visualize and understand things. So as we understand more about scientific concepts, we often use models to help us visualize them and teach them. And that's why we use models. So just a quick refresher about what a scientific theory is. So a scientific theory is based on a preponderance of evidence. That means a whole lot of evidence is needed to support a scientific theory. But scientific theories change or evolve over time as new evidence that is been validated to be valid scientific evidence, and it has been supported by peer-reviewed science, which you guys know what peer-reviewed science means, that the scientists that are experts in the field get to critique the experiments of other scientists and say whether that's the data is good data or not. So what happens in a scientific theory is science can test things in a certain way, and then we can modify our theories. So, scientists would see some kind of observation and then make a hypothesis, right? So a hypothesis is kind of an educated guess. It's going to be a prediction about something based on an observation. So then the scientist is going to do a controlled experiment, right? So he or she would have a control group, and they would have an experimental group, and they would have a dependent variable that they would measure, and they would have an independent variable that they would change on purpose. And so they would look at this and they would say, okay, well, either the data does not support the hypothesis, and so they would then revise their hypothesis and do some more experimentation, or they would say, yes, my data supports my hypothesis, and then they would do another variation of that experiment. And so over and over and over again, and over time, as more data is gathered, then scientists build a scientific theory. So a scientific theory that is important that you know about is the theory of plate tectonics. So this is the theory about how big sheets of rock are constantly moving under our oceans and on our land, and when those rub up against each other, that is what an earthquake is. The theory of relativity, which made Einstein famous because this gave us a relationship between energy and matter. The theory of natural selection, which is also called the theory of evolution, gives us a well-supported theory about how living things change over time in response to their environment. We have the theory of quantum mechanics, which is a crazy mathematical model that helps us to explain the way that atoms behave. And then we have the atomic theory, like what an atom looks like. And so that's what we're going to talk about in this lecture. So the idea of what an atom looks like, our model of an atom, has changed a lot over the centuries. But starting in 400 BC, somebody had an idea of what an atom looked like. And that idea was not tested because this person was a philosopher and they weren't a scientist. But they had an idea of what an atom looked like. And so you maybe have heard of Aristotle. Aristotle was a very famous Greek philosopher. You probably have not heard of a Greek philosopher named Democritus. Well, Aristotle was way more popular and famous than Democritus, who was a peer of his. But it turns out about this idea about atoms, Aristotle was wrong. So what Aristotle thought is he did not believe in atoms. He thought that all materials on Earth and in space were made of a combination of 4 different elements: fire, air, water, and earth. And you could explain everything based on those combinations of elements. Well, it turns out that that was wrong, okay? But he was a pretty smart guy, and he was very famous, and so a lot of people believed what he said. But as it turned out, there was a guy named Democritus, who was a Greek philosopher, as I said, and he had a different idea. He believed that all things were made of little tiny, indivisible parts, and he called those things atomos, which is the Greek name for individual parts. And so that's where we get the name atom. We get it from this idea back in 450 BC that all things were made of little tiny indivisible parts. And so that is that's why we give Democritus credit for that. But of course, Aristotle was way more famous. But as I said, he was wrong. But Democritus was a philosopher. He was not a scientist, and so his theory couldn't be tested. He just had an idea, and it was forgotten for more than 2,000 years. Until there was a guy named John Dalton, who was a scientist living in England in 1803. And John Dalton began to do some experiments on this idea of what is matter made of. And his experiments led him to gather some data, and that data helped him to come up with a theory. And this is his atomic theory. He said elements are made up of tiny indivisible particles called atoms. So this was a nod to Democritus, because Democritus was the guy who came up with this name, even though he couldn't test it. So that was really cool that he called these things atoms after Democritus's idea 2,000 years ago. John Dalton said atoms of the same element are the same, and atoms of different elements are different. So some of these things are still true with our theory today, but some of them are not. You'll see in a minute. Compounds, he said, are formed when atoms are combined. Each atom has a specific number and kind of atom. So a compound would be like H2O. And so John Dalton said, well, hydrogen has 2 parts of hydrogen and 1 part of water. And chemical reactions are arrangements of atoms, but atoms are not created or destroyed or broken apart. So you'll see that some of these things turn out to be right, but some of them are not. So how big is an atom? You watched a video, or you will soon watch a video about how tiny atoms are. A very small drawing a line across a penny would be 800 million atoms. The diameter of an atom is 1 times 10 to the minus 8 centimeters, or what we call 1 angstrom. And 1 angstrom is 10 nanometers. So very, very small. So one of the things that, if I had to tell you what Dalton thought um, that um, an atom looked like, is Dalton. Okay, so let's go back to Dalton in 1803. He thought an atom was kind of like a pool ball. Okay, and when I mean a pool ball, I mean a billiard ball. Okay, so a billiard ball. So he thought they were solid and they were not able to be broken apart. And so that's what he thought an atom looked like. Well, it took about almost 100 years, 90 some years, to a guy named J.J. Thomson. And good old J.J. Thomson found out that there were some parts of Dalton's theory of an atom that were wrong. And this is what he did. So at that time, people had just figured out how to make something called a vacuum tube. And what they did was they took a piece of glass tubing and they sucked all the air out of it. And then they ran an electrical current. We were just learning about electricity then. And we ran an electrical current through this vacuum tube. And interestingly, these vacuum tubes turned out to be what we used to make the first TV tubes, TV set tubes. But back in the day, we didn't really know what these were. But anyway, these vacuum tubes begin to glow. And so what JJ was trying to figure out is what the stuff is that was going through this tube. And so this tube, by the way, was called a cathode ray tube. So these cathode rays had been discovered back in the about 1890s. Okay, and so this was 1897. And what J.J. Thomson did was he looked at this electrical current through this vacuum tube, this cathode ray tube, and it appeared to move from the negative end of the electrode to the positive end. So that was one piece of evidence that he. And then he did something really cool. He added an electrical field. And so what he did in his cathode ray tube is he took a positively charged thing and he saw, lo and behold, that these cathode rays begin to bend towards the positive electrode. And so, of course, he knew that negative and positive things attract each other. And so he thought, I think that these cathode rays are tiny, tiny pieces of an atom that he called electrons. And so J.J. Thomson discovered the electron. He did this by some pretty cool mathematical experiments, but he discovered the electron. And so his theory of the atom changed Dalton's because he said a pool ball, remember Dalton thought that an atom was like a billiard ball, right? Like a pool ball, like solid. And JJ said, no, I think it looks like plum pudding. Okay, so good old J.J. Thomson was from England, and English people like this stuff called plum pudding that has, it's like a pudding, but it has like raisins in it. And so that's what he described. For us, we would say maybe it's kind of like a chocolate chip cookie. And so what J.J. Thomson's model of the atom looked like is the atom had a bunch of positive stuff in it that he said was this green stuff or the pudding. And the electrons, he said, were spread out inside the atom, kind of like chocolate chips in a chocolate chip cookie, or like plums in a plum pudding. And that was how he changed the model of an atom. So that was back in 1897. Now things are starting to change pretty quickly in the land of atomic experimentation. And there was another scientist down in New Zealand named Rutherford. I'm sorry, he did this experimentation in England too, but he was from New Zealand. And this was in 1899, and Rutherford did a very cool experiment called the gold foil experiment. And as a result of this experiment, our idea of what an atom looked like changed again. All right? Because Rutherford discovered the nucleus of an atom. All right? Which is kind of cool. So this is how he did it. He had a lead block, which at this time, scientists were really excited because they had just discovered radioactivity. And polonium is an element that is radioactive. And so what he did was he knew this lead block would block out all the radiation except a little place where these little radioactive particles would come out. And these were called alpha particles. So this was a type of radioactivity that was coming from the polonium, and Rutherford was experimenting with it. He wanted to kind of see if he could learn anything more about the atom by doing this experiment. So what he did was he shot these little alpha particles out of his little polonium gun, so to speak. And he had where these little alpha particles would hit this fluorescent screen, they would make kind of a glow every time they hit this kind of photographic paper. It would make a glow, so they could see where these alpha particles hit. And then what he did was he took some gold. And he took a sheet of gold and hammered it very, 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 very thin. So it was just one layer of gold atoms thick. Okay, so he had these gold atoms that he hammered into a very thin film. And so because of this, he learned something about the atom that we didn't know before. This is what he expected. Okay, so this is Rutherford again. We're talking about Rutherford, and this is what he expected. He expected that these atoms, right, these gold atoms, were like plum pudding, right? So he thought that they had mostly positive material, but there were negative electrons that were spread out in here. And this alpha particle was positive, right? So they knew it was kind of a big positive particle. So what he thought was this alpha particle, this alpha bullet, would go straight through the negative part of the atom, and he could tell that because he could tell where it hit. And so he thought, this is his idea, he thought that all of the alpha particles would hit right there at that spot. And so he sent his graduate students down to do this over and over and over. They were down in a dark basement kind of thing, and they kept shooting these alpha particles, and they kept seeing the glow. And for a while, that's pretty much what happened. And again, he thought that the alpha particles would go straight through. They were positive. He thought they would go straight through the plum pudding model of what J.J. Thomson thought an atom looked like. But this is what happened. One day, his students, his graduate students, came running up the steps and saying, "You're not going to believe this, boss, but one of these alpha particles actually bounced backwards. And the more they did it, every once in a while, they would bounce off at weird angles. He was right that most of the alpha particles, most of these alpha bullets, these alpha particles, would go straight through the gold atoms. Remember? So this is a piece of gold foil, and most of them did go straight through. But every once in a while, one of them shot straight backwards or shot off at an angle, like it was hitting something. And he famously said, "I could not have been more shocked if I took an elephant gun and shot it at a piece of tissue paper and it bounced back." Wow. So what did good old Rutherford conclude from this experiment? He concluded that there is a very, 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 very tiny positive particle inside the atom. And he called this the nucleus. Now, later on, there was another scientist named Chadwick who found out that the nucleus had positive things in it called a proton, and then somebody else found out that there were some neutral things called neutrons that were also in there. But Rutherford discovered the nucleus itself. And he said, well, this is why most of the alpha particles went straight through, because the nucleus is so, 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 so tiny. But every once in a while, one of them would hit and bounce off, or if it was a direct hit, it would bounce straight back. And so that is exactly what we figured out. And they knew that the alpha particles were positive, right? And so positive doesn't like positive, and so that's how they figured out that the atom had a very, very tiny positive center. So our idea of the atom changed again. So then in 1913, there was a guy named Niels Bohr who did some other experiments and a lot of mathematical experiments. And he changed our model of the atom yet again based on the data. And he said, yep, there are these electrons, and there is a very, very tiny positive nucleus, just like J.J. Thomson said and just like Rutherford said, and some things that were just like what Dalton said. But he said the electrons are not like raisins in plum pudding or chocolate chips in a cookie. These electrons, he said, are moving around in an orbit, kind of like planets around the sun. And the orbits are very specific distances from the nucleus. And he called these energy levels. Okay? Now, as it turns out, this explained a lot of the kind of weird behavior that atoms were doing. And it explained it with some math, but that didn't stay that way very long because we found out that there was some other evidence that explained that this is not the way that atoms. So the modern view of the atom started about 1926, and there was a guy named Erwin Schrödinger who figured out with some pretty crazy high-level math that electrons did not go around and around like orbits. They did something different. So everybody agreed by this time, and we call this the modern view of the atom, that an atom was mostly empty space. Remember that if an atom was the size of a football stadium, right? If an atom was the size of a football stadium, the nucleus would be a blueberry, right? On the 50-yard line. So that is how small the nucleus is. And the rest of that football stadium would be empty space. And so the nucleus is where the protons and neutrons are, but it's super, 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 super tiny. And the electron cloud, not orbits, are where you would find an electron. So we call this theory that Schrödinger came up with in 1926 the quantum mechanical model, because it uses some really crazy math called quantum physics. And this is our current view of the atom. So the quantum model differs from Bohr model in a couple of very important ways. So remember, Bohr thought that electrons went around and around and around, just like planets around the sun, around kind of like, electrons going around like that. And we know that's not true. Electrons do not travel in fixed path, but their motion is random. So electrons are just kind of buzzing all over the place, okay? And so Bohr said that electrons are found in orbits around the nucleus. We know that's not true. We know that electrons are found in places called orbitals that are kind of like clouds, where the electron has a high probability of being. The electron could be anywhere because it's buzzing around all over the place, but orbitals are where the electrons probably are. And so these are some pictures of what orbitals look like. These are where electrons would be found. And so electrons would be buzzing around in this area, or buzzing around here, or buzzing around here. Here are some other different shaped orbitals that electrons, they could be out here, but more than likely it's in this area right here. And so we can see that there are some beautiful, atoms are beautiful. And this XYZ is just showing you that these are three-dimensional shapes of what the atom actually looks like. And remember, where is the nucleus? The nucleus would be a teeny, teeny, teeny dot right in the center, right? If this whole atom here was the size of a football stadium, that would be the blueberry right there in the center. And so these beautiful orbitals have amazing shapes. And again, this is described by the mathematics called quantum mechanical physics. And so that is now the view that we have of the atom. So we have gone from, let's see if we can figure all this out. We have gone from the idea in 450 BC, right? We had Democritus come up with the idea of an atom. In 1803, we had Dalton come up with the idea that atoms were actually structures, and different atoms make up different elements. Then we had J.J. Thomson discover the electron in 1897. And then we had Rutherford, and with the gold foil experiment just a couple years later, discover the nucleus. And then in 1913, we had the Niels Bohr model, where he said atoms, the nucleus was very small, but electrons traveled around in orbits, kind of like planets around the sun. And now, starting in about 1926, we come up with this idea of the quantum mechanical theory, which is our current way, our current model of what an atom looks like. And atoms, if you could see them, would have these beautiful orbital clouds where the electrons are buzzing around, and very, 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 very tiny nucleus where the protons and neutrons are. And of course, we have discovered a lot more subatomic particles like bosons and really cool things like that. But that is what you'll learn when you take physics. So hopefully this has been helpful and you've enjoyed learning about the history of the atom.